So visually, how can you tell where there is a relative or a local maximum or minimum value? Well, kind of just by looking at this, it kind of depends on the function in a lot of ways, right? How clearly are those points drawn? How easy is it to kind of read what those values are? And in future classes, there's ways to solve for this. All that we're looking at right now, though, is just by kind of eyeballing it, what can we tell? And a good way to check this, a good kind of test for this, is to see if we go if we change directions from either increasing to decreasing or from decreasing to increasing. So remember on the last set of information, the last set of pages, that's what we were talking about, right? How to identify intervals where we increase or decrease. But those turning points, those places where we go from one to the other, those are actually representing our maximum and our minimum values. So if we were to take this interval and say we were decreasing, right, from here to here, but then do you see that there's a turning point and we actually change direction and we move to increasing up until right about here, right? Now, again, it depends on the graph. I would argue it's a little hard to read exactly what this point is, right? Maybe something like negative 1.5. Again, it's not super clear because of the way the graph is drawn, but because we went from decreasing to increasing right after, that makes this point specifically a local minimum, right? Absolute maximums and minimums, the test mostly works. It mostly still follows. So for example, by looking at this, I can see there are no other points. And we'll talk about this a little bit more in future examples. This also makes it an absolute minimum. We'll talk about how to distinguish and tell the difference between those in the next video. And then very similar to that, up here, we already said that we're increasing on this green portion. So what if we're decreasing again from here to here? Well, do we see that that makes this, and this one's pretty clearly at 2, right? That makes this a local maximum, right? Because we went from increasing to decreasing like this. So this particular f of x value, I should say at f of 2. Local maximum, and this is f of 2. And back here we could say this is the local minimum. This is f of, again, I'm going to go with negative 1.5. We just do the best we can in this class, so I'll make sure graphs and all that are labeled when it comes to an exam. And then very similar to that first group we looked at, we went from decreasing, right? That's that blue interval. And then we finished this off by increasing again. And that turning point between the two, that's this value right here. It actually looks a little bit past 4. This would be another local minimum, okay? And this is f of, it's a little past 4. We can put maybe 4.1 or 4.2. It's a little beyond, again, hard to read just because of the way the graph is structured, okay? But do you see how you can kind of visually point out where those pieces are located? I would argue that this is still local, as well as up here, this is still local. There are very clearly other values that are taller than this local maximum, right? There's definitely f of x values as this graph moves higher and higher up, right? So it's not the absolute maximum, it's not the tallest of all of them, but compared to its neighborhood, it's tallest. And then same thing for down here. It's definitely local because there are for sure other f of x values that are lower, like this other one we pointed out, but even ones like right here, right? All of those function values get used and they're definitely smaller than this one, but compared to its neighbors around it, it's the smallest of the group. Okay.